It's really great to have Tengyu Ma here today. So Tengyu did his undergrad at Tsinghua University, part of Andy Yao's pilot class. He's a grad student at Princeton, where his advisor is Sanjeev Arora. And in the last couple of years, he's had a string of really remarkable results in non-convex optimization, and I'm excited to have him speak here.
Okay. Thanks for the introduction. Thanks for coming. So I'm going to talk about non-convex understanding non-convex method in machine learning. So let me start by talking a bit about what I see as some algorithmic challenges in machine learning. One of them stems from the fact that the models we are using these days are often very complex. And this makes the natural learning of functions non-convex and sometimes intractable in the worst case. And moreover, we are using these complex models on huge data sets. The dimension of the model, the dimension of the data, the size of the data sets are both very high. This requires us to use scalable algorithms. For example, deep learning is one of the examples where we'll use complex models successfully on tasks in computer vision, natural language processing, etc. For example, in computer vision, we have this ImageNet data set, which consists of 1.2 million examples. And the task is classify these images into 1,000 labels. One of the ways to do it is to use this giant neural network called GoogleNet, which consists of 22 layers of different type. Some of them are convolutional layers, some of them are fluid connected layers, some of these are batch normalization layers. There are totally 5 million parameters to describe the network. The algorithm question here is to find the best neural network, the best set of parameters that fits the given labels and data the most accurately. So you can see that how complicated the training of these kind of models could be, and in fact it takes like 2 weeks to train it on a single typical GPU. We can use even more complex models like a recurrent neural net to attack the task of machine translation. A recurrent network, if you annually through time, can be drawn like this with a little bit of simplification. So this is kind of like a computational graph. The rectangles denote vectors, and the arrows denote dependencies between these vectors. We encode the words as indicator vectors and pass it through this computational graph, and we get a sequence of output as output. So again, the models are very complex, and in this case, the number of parameters could be more than hundreds of millions. So you can see that towards understanding deep learning, we are facing the algorithmic question of understanding how to train these models. So how do we do this in practice? It turns out that to do it reasonably well in practice, we only need to use stochastic gradient descent on the natural non-convex learning object functions. Just to remind us what gradient descent and stochastic gradient descent are. So gradient descent is the greedy local search algorithm. We move towards the reverse direction of the gradient because that's the steepest direction you can go downhill. And stochastic gradient descent is basically a noisy variant where the computation of the gradient is noisy. This is mostly for speeding up. And for the purpose of this talk, we can basically think of them as local search algorithm. So the nice thing about stochastic gradient descent is that it is simple and scalable. It is easy to implement because we can just use some auto differentiation package to compute the gradient. And moreover, the most surprisingly, it often returns high quality solutions, which are often believed to be approximate global minima. The main mystery here is that why this can always happen. A priori, local search algorithm could get stuck at a bad local minimum. For example, we have this one-dimensional case here. There's a global minimum on the right, and there's a local minimum on the left-hand side, so which is not a global minimum. Let's say suppose we start here, we do gradient descent. We just go downhill, we go left, and finally, we are going to get stuck at this bad local minimum. So this is why I'm very interested in answering the question, why does non-convex optimization can work so well on training so many machine learning models, and how can we improve it by making it more powerful and applicable? So in this talk, I'm going to discuss kind of 2 ideas along this line. One of them is to address the question of why, and the other is more about addressing the question of how can we make it more powerful and applicable. So the first idea is that we can analyze the non-convex optimization via the analysis of the optimization landscape. It has been conjectured that many of the object functions in machine learning has some nice geometrical properties that implies convergence to a global minimum. For example, one of them is all local minima are global minima. This has been conjectured in the context of neural networks by Kremenska et al. Basically, this is saying that, okay, the object functions that I've just shown you, This doesn't happen very often in machine learning setting. And what really happens is this kind of W-shaped function where there's no bad local minima. There are two local minima, and they are both global minima in this case. So the reason why this makes us happy is that many local search algorithms converge to a local minimum or approximate local minimum with arbitrary initialization in polynomial time. So you may wonder how often this can happen in machine learning setting or in general. And in this talk, we are going to establish this geometrical property for the object functions of matrix completion and some simplified versions of neural nets. So this sounds nice. However, the natural question is, what if the object functions we are dealing with doesn't have this nice geometrical property? Can we still do something for it? So the next idea is more about to address this question. So the idea is that we can improve the landscape while changing the object function. There are multiple ways to change object functions. One of them is re-parameterization of the model. Let me just give you this very toy example to convince you that re-parameterization does make a difference. Let's say we have this convex object functions x minus 1 squared. This is probably the nicest object functions we can hope to optimize, so we are very happy here. And let's try to re-parameterize it. Let's say we take x to be y times z and x to be y over z. And then you can see that the landscape of the object function becomes very different. It becomes non-convex. And given this picture in hand, I think it makes sense to define, remind us some of the terms in calculus that we're going to use in this talk. A critical point is a point with zero gradient. And these two are both critical points. One of them is a local minima, and the other is a saddle point. A saddle point is a critical point that is not a local optima. And we can see that by re-parameterization, we create this additional critical points and the local minima and change the landscape of the object function. Of course, if you look at it in the reverse direction, if you view the left-hand side as the re-parameterization of the object function on the right-hand side, it makes the object functions nicer. This is just a toy example. Later in the talk, I'm going to give a more realistic example that shows that re-parameterization does help in machine learning settings. So there's another way to change the model and change the object function, which is over-parameterization. Let me just give you this kind of experiments, synthetic experiments that shows you over-parameterization empirically helps. So what I'm going to do is that we're going to generate synthetic examples by a fixed two-layer nets with 100 hidden nodes. So we have this network. The input dimension and label dimension don't really matter. What matters is we have 100 hidden units in the middle layer. We generate effectively infinite number of examples from this network. And then we kind of forget the ground truth network, and we just train with the given examples. So we train with the same model with 100 nodes in the middle layer. So in this case, we can expect that the global minimum has error 0 because there exists a neural network that fits all of the examples exactly. That's the one that we use to generate examples. However, if you train it using stochastic descent, what you see is that the error doesn't go to 0 at the end. So it seems that we converge to a bad local minimum. This suggests that the object functions we are dealing with here doesn't have the geometrical property that all local minima are global minima. So, however, we can fix this problem very easily by training with 400 hidden units in the middle layer. So we have, the same input dimension, output dimension. The only thing we change is that we increase the size of the middle layer. And now, if you train it using stochastic descent, you see that error suddenly drops to 0 very quickly. And we know this is a global minimum because the error cannot go below 0. And if you see error 0, then that means it's a global minimum. So this suggests that over-parameterization makes the object functions easier to optimize. We couldn't formally prove anything about this special case, but what we can do in this talk is that we can show probably re-parameterization and over-parameterization are beneficial in the simplified versions of neural nets. Re-parameterization is beneficial in the simplified version of deep nets, and over-parameterization is beneficial in the simplified version of recurrent nets. So these are some overview of this talk. So part of my research aims to understand the training aspects of deep learning. Or a little bit more broadly speaking, how do we train complex models using non-convex methods? Along this line, I have been working on several questions like dictionary learning, deep sparse autoencoders, tensor decomposition. And in this talk, I'm going to talk about matrix completion and the simplified versions of recurrent nets and deep nets. And the point in matrix completion is that we have this idea one where we show that the matrix completion of object functions has the nice geometric property. And the point about the neural networks is that over-parameterization and re-parameterization do help by the training of making the object functions nicer to optimize. Let me start with matrix completion. So the setup is pretty simple. There is a low-rank matrix M. We only observe a random subset of the entries of this matrix M. And our goal is to recover the rest of the entries. This is a famous question in statistics and machine learning. The typical applications include recommender systems and collaborative filtering. So for example, we have this user item preference matrix. Each entry is the user i's rating to the item j. We can collect a few entries of this matrix, and our goal is to recover the rest of the ratings so that we can recommend the right items to the right users. There have been a lot of beautiful papers on using convex relaxations or nuclear minimizations to solve this problem. So this has the strongest theoretical guarantees with optimal sample complexity. However, the only drawback is that it often requires solving semi-definite programming, which means that the runtime is a little bit slow. So in practice, what people often do is to use non-convex optimization like stochastic descent or alternating least squares to solve the problem. And this also motivated a lot of study of non-convex optimization for this problem, a lot of theoretical studies of non-convex optimization for this problem. However, most of these papers require good initializations to start with. And in fact, it is known that the initializations is sufficiently good so that functions actually convex locally around a neighborhood that contains initialization. In other words, most of these papers are basically analyzing non-convex methods for convex functions. What we are going to do is we are going to start with arbitrary initialization and converge to a global minimum. So let me have some basic notation set up. So we assume the matrix M is of the form M is equal to Z times Z transpose. So here Z is this tall matrix of dimension D times R. D is considered to be much, much larger than R. This makes the matrix M low rank, symmetric, and positive semi-definite. So some of you may notice that this is the symmetrical version of this matrix completion problem. In practice, the asymmetric version is more important. However, for theoretical simplicity, we started with the symmetric version. And now there are follow-up works that have shown that the same techniques or similar techniques can be used for analyzing the asymmetric case as well. Regarding the observation model, we assume that each entry is observed with probability p independently. And we're going to use omega to denote the set of observed entries. We're going to use non-convex optimization. We introduce this variable x, which has the same shape as z. So x has the dimension d times r. And indeed, x equal to z is one of the intended solutions. And we just write down the straightforward non-convex functions, which is the sum of the L2 loss over the observed entries. Let me parse this for you. So xx transpose is our prediction for the matrix M. Xx transpose sub ij is ij's prediction that we make. Mij is observation. And we compare them. We take the square, and we take the sum over the observed entries. So we're going to analyze this object function. We're going to analyze the landscape of it. So our main theorem assumes that under standard assumptions about matrix completion, like incoherent and while conditioning, which I'm going to sweep under the rug, we also assume that we observe at least d times r to the 6 observed entries. So here we get optimal dependency on dimension d, but we didn't get optimal dependencies on the rank r. Although d is much larger than r, so we thought to get the right dependency on d is the first priority. And under these assumptions, with high probability over the choice of the observation set, we have that all local minima of the object function f are global minima. So we can also establish other useful geometric properties of this object function. For example, f is not convex. There exists saddle points, which are not local optima. And also, there's no degenerate saddle point, meaning every saddle point has a strictly negative has a direction with strictly negative curvature. This no degenerate saddle point condition, together with our main theorem, implies that stochastic descent converges to a global minimum with arbitrary initialization in polynomial time. So these are our main results. And so why this can be true and how do we analyze it? So towards building some intuition, let's start with the full observation case as some warm-up. So let's consider the simplistic case where we observe all of the entries. So in this case, the problem itself is not interesting because we observed all of the entries. There's nothing left to recover. However, the object functions that looks for the underlying factor z is still interesting to study. So we call it g of x, which is the sum of the loss over all of the entries. So some of you may notice that this is basically the SVD of objective functions for the matrix M. So here we certainly observe enough entries. So this is a subcase of our main theorem. So it's better that this object functions also has the same geometrical property. And this is indeed true. And let me show you by picture. So with dimension is 1 and rank is 1, we have that object functions look at this. This is exactly what I've showed you before in one of the introduction slides. And when dimension is 2 and rank is 1, then this is how the object functions looks like. So we have two local minima, and they are both global minima. Actually, this case has been analyzed theoretically at least twice in the literature by Baldin, Hornick, and Schreiber and Yakola. So we have some reasonable understanding about the full observation case. So the main challenge in this paper is that how do we generalize our intuition about full observation case to a partial observation case? How do we generalize our proof for the full observation case to a partial observation case, or in other words? So our analysis is pretty simple, actually. So it's based on two simple ideas. So the first one is that linear statements are preserved by random sampling of the entries of the matrix. By that, what I mean is that suppose you consider some general matrix W, and you take a partial sum over the observed entries. And this partial sum should track the original sum up to some scaling factor p pretty accurately if you have enough observations entries in omega. So we're going to call this sum of wij of the observed entries a linear statement. And the second observation is that combinations of linear statements are still preserved by random sampling. You can take two statements like this, you take the sum of them, they are preserved by random sampling. You can take the product of them, they are still preserved by random sampling. So these two simple observations motivated us to the high-level plan that we are going to prove the full observation case by combining this linear statement. Suppose we can do that, then the same proof will also generalize to partial observation case without much modification. So let me just give you an example. So let's say suppose we have some statement like this. A sum of wij over all of the entries is 0 in the full observation case. Suppose we have such statement, then correspondingly, in the partial observation case, we can write sum of wij over the observed entry is approximately equal to 0. And we can also write inequalities. Let's say we have sum of wij is larger than 0. This is sum over all of the entries in the full observation case. Then correspondingly, we can write sum of wij over the observed entries is approximately larger than 0, up to some approximation error. We can do this so on and so forth. And finally, suppose we combine the statements on the left-hand side and get some conclusion. And then you can use the same combination and get similar conclusions for the partial observation case. So in some sense, this is the strategy is basically like this. You have it's kind of like building a rocket from parts. You have this rocket called all local minima, or global minima. And suppose you can build this rocket using only linear parts, and each linear part is preserved by random sampling, then this whole rocket is preserved by random sampling, and the whole proof generalized to a partial observation case. So I like to end the matrix completion part by summarizing the analysis strategy and with a philosophical remark. So our analysis strategy is like this. So first of all, we warm up with the full observation case. And actually, we don't have to do this because there are analyses in the literature. And the second part is essential. We need to redo step 1 by combining linear statements. And suppose we can redo step 1 by combining linear statement, then the next thing is that the third step is automatic. because the same proof for the full observing case will generalize to partial observing case automatically. So a philosophical discussion is that restricted proof techniques sometimes may be good. So here we restrict ourselves to using only linear statement. And the statistical gain we have is that the same proof will generalize to partial observation case. And actually, this is also the same idea behind sum of squares proofs. This is proof techniques in algebraic geometry. It is a restricted proof techniques, but it can be found efficiently. And actually, I got inspired by these proof techniques a lot. And I've also been working on some squares proofs, some squares relaxations for machine learning problems, including tensor decomposition and sparse PCA. So this is all I want to say about matrix completion. And let me move on to linearized recurrent net next. So, OK, so let me talk about recurrent net and the linearized version of it. So the point here is that over-parameterization can make the optimization easier. Let me start by making the point that recurrent neural net is a subcase of dynamical systems. So in both recurrent net and dynamical system, the input is a sequence of scalars of vectors, and output is a sequence of scalars and vectors as well. The output depends on the input via a sequence of hidden states, h0 up to ht. You can think of this as the memory of the system. Sometimes a recurrent net is drawn like this. So these rectangles denote these vectors. For example, the blue rectangles denote the sequence of states. And the green rectangles denote the sequence of inputs. And these arrows denote dependencies between these vectors. So mathematically, what it is that a dynamic system is a system characterized like this. So ht at time t, this is hidden state at time t, is a function of the hidden state at time t-1 and the input at time t. And output at time t is a function of the state at time t. And in recurrent net, basically what happens is that we parameterize f and g by neural nets. So the learning task here is that we are given samples of input and output pairs that are generated by some system, and our goal is to predict the output of the unseen examples. Even though recurrent net, our main motivation was to study recurrent net, it turns out that the problem of learning dynamical systems have been studied for quite a while in 3 communities. In time series, in statistics, this is often called a state space method, which was originally proposed by Kalman in 1969. There have been a lot of books that cover different techniques about state space methods with a lot of applications in econometrics. In control theory, this is often called system identification, meaning we want to identify the parameters of the system. There have been a rich set of special purpose tools and techniques developed in the past several decades, and many of them have been implemented in system ID toolbox in MATLAB. In machine learning, we often call this these days sequence-to-sequence learning. And the way that we are solving it is strikingly simple. We just use stochastic descent with backpropagation through time. And the way that we implement it is also strikingly simple. We just use auto-differentiation package. We describe the model in a package, and with one line of code, you can get a gradient. With another line of code, you can get optimizer. And this talk, I'm going to analyze stochastic descent for the problem of learning linear dynamical system. Although part of our tools come from control theory. I'm not an expert in statistics and control theory, but I do believe that these tools can be combined together. These tools in different fields can be combined together and solve problems in other fields. Given this problem has been studied in different fields, it's not surprising that it also has a lot of applications to other scientific areas. So for example, the original motivation of Kalman was to model mechanical aerospace system. Time series has a lot of applications in econometrics. System identification has a lot of influence to system biology and environmental system. In computer science, the applications include natural language processing, video understanding, and reinforcement learning. These are all situations where the input and output are both sequences. For example, in reinforcement learning, in some sense, we need to learn the model and control the model simultaneously. So what we are going to do today is only learning linear dynamical system using stochastic descent. So this is as a start, as an initial step towards understanding learning dynamical system. And this turns out to be also the same as a linearized recurrent net. But that what I mean is basically we parameterize this state-to-state transition function by linear functions, and also the observation model is also linear. So ht, the hidden state at time t, is a linear function of state at time t-1 and input at time t, and the observation is a linear function of the state at time t. And plus a noise vector Ct. So here A, B, C are unknown parameters with compatible dimensions, and Ct is a noise vector. So for the simplicity of this talk, we're going to assume work with a single input, single output system. So xt and yt are both scalars at each time. And the memory size can be in high dimension. So the dimension of the hidden state t at time t can be dimension d. So we're going to use stochastic descent. So we introduce these training parameters, a hat, b hat, c hat. So these are variables in our optimization. And in our training system, basically we just replace a, b, c by a hat, b hat, c hat. ht hat is the state at time t in our training system, and y hat t is the prediction that we make at time t. So given one example, we can define the loss function. This is the empirical risk for one example, which is the L2 loss between y hat and y. So y hat is our prediction, and y is the true observation, true output. And we can also define the population risk, which is the expectation of the empirical risk over the randomness of the examples. So basically, this is the object functions that you can optimize when you have infinite number of examples. So recall, previously, when we talk about matrix completion, we have this kind of machinery that connects the geometric properties of the empirical risk, which is the partial observation case in matrix completion, to the geometric property of the population risk, which is the full observation case in matrix completion. So here we can still do that. We can show that empirical risk and population risk have very similar geometrical property. Although here, even the geometric property of the population risk is not well understood yet. So that's why we start with the landscape of the population risk. So towards analyzing the landscape, so we are working in the setting that xt has mean 0 and variance 1, and they are pairwise uncorrelated. And then our main theorem says that we assume a strong stability condition on the spectrum of the matrix A of the ground truth system, which I'm going to define in the next slide. And then under this assumption, all local minima of the population risk F are global minima. So this also has the algorithmic implication that stochastic descent converges to a global minimum in polynomial time. So here the crucial thing is, what is this strong stability conditions? Let me define it for you next. So towards doing that, I may first discuss the kind of default assumptions that we kind of want to make about this system. This is so-called bounded input, bounded output stability. So as the name suggests, so if you give the system a sequence bounded input, you expect the output to have a bounded norm that only depends on the system. So this is kind of a default assumption because an unstable system has exploding outputs and exploding gradients. And also it's not quite clear why we want to learn an unstable system at first place. This turns out to mathematically corresponds to the eigenvalues of the matrix A are inside the unit circle. So this matrix is not a symmetric, so the eigenvalues could be in complex numbers. And they are in the unit circle in the complex plane. So the problem with this condition is that this characterization is that in most of the natural parameterization, probably almost all natural parameterization, the set of stable system is not convex. So the set of stable system is non-convex. And this prevents us to have a efficient algorithm project back to this system when we use stochastic descent. So what we are going to do is that we're going to design a convex set of strongly stable system. So this is a subset of the set of stable system, and we assume that the true system belongs to this convex set. And if this happens, then we can use local search algorithm. Another nice property is that in this set, the landscape is good. There's no bad local minima. So all local minima are global. And when this happens, then we can use local search algorithm with projection to the convex set. So basically what we do is we start from somewhere here, and we do one step, of gradient descent or local search, and we do another step, we go out of the site, and then we project back. We do another step, gradient descent, we project back. We follow the gradient descent, and finally, we're going to converge to a true system. So here, the kind of key question is how large this subset is. So I won't give you the exact definition of this subset. It's a reasonably large set, but admittedly, it's still a stringent assumption on the true system. So this brings us to the next question. What if the true system is not strongly stable? So what if the true system is here, which is not in a strongly stable set? Can we still do something for it? And this is when the power of over-parameterization comes into play. Our idea is that we are going to over-parameterize our training system with higher dimensional hidden states. So our original dimension is d, and when we train it, we use dimension d prime, which is larger than d. And this means that we are going to introduce redundancies in the parameterization. And redundancies in parameterization basically means two things intuitively. A, it means that we have kind of more strongly stable system because we are in higher dimensional space. And B, it means that we have more candidate solutions because of the redundancy of the parameterization. Basically, what happens in a higher dimensional space is that we have a family of equivalent systems which are equivalent to the original one in terms of the input-output behavior. And as long as this family of equivalent systems intersect with the set of strongly stable systems at some point theta prime, then what happens is that we'll find an over-parameterized strongly stable system theta prime if it exists. So this is why over-parameterization helps, and we can also quantify how much it helps. We can show that such over-parameterized strongly stable system exists with dimension d prime, which is not much larger than d, under much milder assumptions on the true system. So before we assume the true system is strongly stable, and now we only need to assume, in some sense, the true system doesn't have repeated eigenvalues in the matrix A. So let me show you some of the simulation experiments that shows the power of over-parameterization empirically. So what I'm doing here is that I'm going to generate data from a stable system, from a system that is stable but not strongly stable. And this is a system of dimension d is 40. So first of all, let me tell you that if we train with dimension 80, so we over-parameterize with factor of 2, and with projection to the strongly stable set, then the error goes to 0 nicely. This is test error. So, and next, suppose we train with dimension 40, and we don't do projection to the strongly stable set because the true system is not strongly stable. And then what happens is that basically the error starts to drop at the beginning, and then at some point it goes to infinity. It returns NaN. So basically what happens is that when you run stochastic descent without a projection, at some point stochastic descent will just wander into some unstable system. And as soon as you hit one unstable system, the error starts to blow up and the gradients explodes, and very soon we get infinity error and gradients.
But if you train it at 40 and project back, is it okay?
Yes, so that's this curve. So if you train with dimension 40 and project back to the strongly stable set, you should expect that it doesn't work because the true system is not strongly stable, and you do projection anyway. So that's why we see that we have underfitting here, and the error doesn't go to 0. All right, so this is all I want to say about recurrent net. And next, let me talk about simplified version of deep nets, where we show that re-parameterization also helps. So speaking of deep nets or deep learning, one of the natural questions to ask is whether it's always true that the deeper is always better. It turns out that the answer is, well, it depends. So it depends on what architecture, what models you are using. So suppose we use standard feed-forward convolutional nets, then actually it's not true. It's even worse when you use, sometimes you use more layers. It's very hard to train any deep nets more than 20 layers. So, and on the other side, suppose you use the so-called residual net, which I'm going to define for you in a minute, then yes, it's always almost true that deeper is better. And let me emphasize that this is empirically true for both training and testing error. So basically what happens on the left is not just, you over-parameterize and you have too many parameters, it overfits and test error goes up. Even the training error also goes up. So this suggests that the optimization plays an important role here. Let me define these networks for you. So standard feed-forward net with a little bit simplification basically look like this. So you have a bunch of hidden layers, you have a bunch of matrices, and the layer at hidden state at layer I is a ReLU of AI times HI minus 1. So here ReLU is a coordinate-wise activation function. Basically ReLU on one coordinate is max of x and 0. On the other side, a residual net, which was proposed by He et al., is as follows. So only the changes is that we add these identity connections from layer 0 to layer 2, layer 2 to layer 4. Mathematically, what I mean is that the definition of H1 remains the same, and definition of H2 becomes ReLU of A2 times H1 plus identity times H0. And we do this for H4 as well, right? H4 is the original H4 plus identity times H2, and so on and so forth. So the original motivation of He et al. Was that it is more natural to represent identity mapping using residual nets. Because using residual nets, if you want to represent identity mapping, you only need to take all of the A's to be 0. And on the other side, if you want to represent identity functions on the other side, it's a little bit more complicated. You can still do it, but it's a little bit more sophisticated. Actually, it turns out that these two models have the same representational power up to some constant factor change of hyperparameters. So they have almost the same representational power, and this seems to suggest that the difference between the optimization comes from, the difference between the error comes from really the optimization perspective. So we try to explain this using the very linearized version. So we couldn't prove the nonlinear version. So we start with a very simplified model for first-cut understanding about this regarding this phenomenon. So we use the linearized deep nets. By that, what I mean is that we got just remove all of the ReLUs from the architectures. So HI is a linear transformation of HI minus 1 on the left-hand side, and on right-hand side is a linear transformation of H1 plus identity times H0. So, in this case, basically the model itself, are not interesting at all, because both of these two cases just represent linear functions, and of course they have the same representational power. However, the optimization perspective is still interesting, because if you want to optimize in the same space, in the A space, there are still non-convex optimization. So, and we can formally distinguish these two cases. So what we can show is that for the optimization problem on the left-hand side, if you want to train this linearized deep nets, the optimization landscape has degenerate saddle points, meaning points with 0 gradient, 0 Hessian, and 0 higher order derivatives. So these are presumably very bad points for local search algorithm, because the local geometric information, property doesn't give you, information about where you should go. On the other side, we can show that all critical points with small norm are global minima. This basically means that you only need to converge to a critical point, and then it is a global minima. And also, this small norm assumption is not a restriction, because there exists a global minimum with small norm if you have deep enough network. So this shows that re-parameterization does improve the optimization landscape. All right, so this is all I want to talk about. All I wanted to talk about the optimization. So next, let me spend 3 to 5 minutes to discuss a little bit about some of my other work along the line of understanding the modeling aspects of machine learning or deep learning. So what I've told you is that changing the model can change the object function. Changing the model slightly can change the object function and make the optimization easier. And here the message is that using a different and interpreted model may also make the problem easier so that we don't have to even train those complex models like recurrent net or LSTM. So we're going to discuss this in the context of semantic embeddings. So let me start by talking about semantic embeddings for words. So what we would like to do is we would like to represent words by vectors in Euclidean space that capture semantic meanings. By capturing semantic meanings, there could be multiple criteria. For example, one of the criterion is that similar words have closed vectors. So, for example, if you have these 3 words about countries, then probably they should be assigned to similar vectors in the Euclidean space. And another criterion could be difference of embeddings captures relationship. So, for example, suppose we take the difference between the embeddings of the country and the embedding of the corresponding capital, then the difference probably should be aligned to some special direction which corresponds to the country-capital relationship. So if you can do this, then we can hope to use this as features for many other NLP tasks. And actually, this has already been the case. There are lots of applications of these word embeddings in many other NLP tasks. What we found theoretically surprising is that there are several different and successful methods that can produce these embeddings with these desired geometrical properties. And these methods are kind of different. So there are 2, like RNN language model, word-to-vect. These are kind of based on RNN. And GLOF and PMI are based on matrix factorization. So the kind of questions that we want to understand is that why can these different methods produce successful embeddings even without enforcing these properties empirically, explicitly? So our explanation is via a generative model for the text. So our general model is like this. So we have a latent context vector, C sub t, which tries to model what we are thinking in our mind. So basically, this vector CT changes slowly each time, and it tries to model the context, the theme in our mind when we write the document. And at each time, given the context vector, we are going to generate the word via log linear model. So the nice thing about this model is that we can explain theoretically the previous methods in the sense that we can show the previous methods are different ways to train our models. So basically, word-to-vect is an EM algorithm for our model, and GLOF is a moment method for training our model. And we can also explain why the difference of the embeddings captures relation. Besides explanation, what I'm very excited about this is that it also allows extensions to other settings. For example, we can extend this to multiple embeddings for polysemous words with multiple meanings. And we can also extend it to embeddings of sentences, which I'm going to discuss briefly in the next slide. So what do we do if you want to embed a sentence to a Euclidean vector? If you believe in our generative model, then the kind of natural choice is that we are going to, given the sentence, we're going to infer the context vector and use the average of the context vector as the embedding. This sounds pretty natural because the context vector is supposed to model the context with our thinking in our mind when we write a sentence. So it sounds reasonable to use that as the representation of the sentence. It turns out that even this simple idea is a tough-to-beat baseline, which can be better than straightforward uses of RNN and LSTM. We tested on several data sets. One of them is to predict similarities of 2 sentences by the angles between the embeddings of the sentences. And you can see that some variant of our methods can do better than a bunch of other deep learning-based methods like DAN, deep averaging network, RNN, LSTM, and some variants of LSTM and skip thoughts. And we have tested this on other similar data sets like entailment data set or sentiment analysis data set like SNI data set from Stanford. And we see similar results. So we are doing better than straightforward uses of RNN and LSTM, but we are not doing much better, or we're not doing better than like the most sophisticated methods which uses synthetic information and ordering information. One of the features of our method is that we use very few label data, and sometimes even no any label data is used. And this makes this method very applicable to settings where we have not enough label data. For example, undergrad at Princeton took our embedding and used it for establishing the mapping between fMRI data and text. So basically, he used these embeddings for the features of text and map it to the fMRI data. All right, so let me tell you a bit about the big picture of my work. So I'm interested in machine learning, and especially the theoretical aspects of machine learning. My work ranges from the modeling aspects towards the algorithm aspects. So what I've told you a bit about is the optimization landscape with a focus on matrix completion and simplified versions of neural networks. Along this line, I've been working on tensor dictionary learning and tensor decompositions just towards developing more mathematical tools to characterize the landscape of the average function. And I've also told you a bit about our work on semantic embeddings, like the sentence embeddings and the word embeddings. Actually, in the word embeddings, we are using a variant of the average functions that we can analyze in matrix completion. We've also worked on the embeddings for senses, where we used the algorithm techniques we developed in the dictionary learning paper to train the models. So I've also worked on structural results for deep learning about sparse autoencoders. And actually, the authors of the GoogleNet cited us as inspirations for the design of the network. I've also worked on several questions along the line of provable algorithms for representation learning. For example, we have this encoding-decoding-based framework for unsparse learning where we can solve some questions that we couldn't solve in the usual framework. And this also connects to sparse autoencoders. I've also worked on topic models and noisy or Bayesian net, where actually we use ideas that we learn from word embeddings and the algorithm ideas we learn from tensor decomposition. On the very algorithmic side, I've also worked on sum of squares algorithm for machine learning, like tensor decomposition, dictionary learning, and lower bounds for machine learning problems like sparse PCA. I've also worked a bit on distributed algorithms like optimization and communication lower bounds. So I fully plan to work on most of these directions in future. And let me tell you a bit about other broader directions I like to work on in future. One of them is better understanding deep learning and make it better. So what is most relevant to this talk is whether we can develop more mathematical tools to characterize the optimization landscape. And another intriguing question about deep learning is whether we can understand generalization theory better for deep nets. It turns out that we don't quite know how to use the classical statistical learning theory to explain the behavior we observed in deep nets yet. And another sub-question here is whether we can incorporate prior knowledge systematically in a deep learning system. So, convolutional net is a way to, incorporate the prior knowledge that the images are translation invariant. And I was wondering whether we can have more systematic ways to incorporate prior knowledge. So another broader direction is representation learning. I think we agree on that. There's a lot of unlabeled data, so we should use them in some way. And also, I believe that some of the lessons that we learn from control theory and the learning linear dynamical system paper can be useful for developing some new tools and theory for reinforcement learning. All right, so as a summary of this talk, so first of all, we showed that without convexity, average functions in machine learning can still have nice geometric property that allows efficient optimization. And second, we showed that changing the parameterization can improve the landscape. And third, we briefly discussed that changing the models can also simplify the learning problem so that we don't necessarily have to train complex models like RNN and LSTM in certain situations. I'll stop here. Thank you.
Hello. So, yeah, it's really interesting talk, and I really like how you combine kind of the topics in many ways of representation learning and understanding kind of the loss landscape of these problems. Have you considered at all what using kind of, so you talk about unlabeled data, have you considered using kind of success at a task as a means of using unlabeled data, right? Because that could let you set your own optimization landscape by setting that task. So for instance, we talked about embeddings. In NLP, there's also something called segmentation, right? And you can measure segmentation by decoding using segmentation and then doing language modeling. And so that could, I don't know how exactly that optimization landscape would work, but looking at that, right, you could set your own optimization landscape to do kind of unsupervised learning. So I'm wondering if you have any kind of thoughts on how to push forward unsupervised learning in that kind of way.
Just to repeat the question, I guess the question is about whether we considered using kind of label data of the downstream tasks to do better unsupervised learning. I think we haven't done that. We test our unsupervised learning algorithm on the downstream, application tasks. We didn't use them that much to train our, unsupervised learning algorithms, to train our unsupervised learning models. So I think definitely that's an interesting question. Although in some sense, probably the ideal case for unsupervised learning is that we don't want to use that much supervised learning data set, because we hope that our representation can be useful for many tasks, not just one task. But of course, using them is also helpful, especially in the context of semi-supervised learning. But we haven't thought too much about it.
You showed that over-parameterization can help in optimization. Can you say something about how that affects generalization?
Yeah, so of course, if you over-parameterize too much, you're going to have overfitting issues. So what we had in a talk about the linear dynamic system case is that we only need to over-parameterize by a factor of log factor or a constant factor, depending on what kind of cases you are dealing with. So, and that's kind of fun in some sense because, we don't over-parameterize that much. I guess there are other situations which we believe probably we need to over-parameterize even more to be more than the number of examples. This seems to be fine in deep learning settings. We don't quite understand why it can happen yet. Yeah.
On a related note, you showed that in some settings all local optima are global optima.
Yeah.
So I assume you mean global optima for the training error.
There we talk about the global optima, the local optima of the population risk, and the population risk is close enough to the training, the empirical risk. So it's also true for the empirical risk.
So some theory assumes independent and uniform probability of observations, and that's not usually the case. So can you comment how would you tackle the other more real cases?
Yeah, definitely generalizing all of this to more realistic settings are very interesting questions. Yeah, we don't really know how to deal with more realistic settings yet, but I do believe some of these ideas can be useful. Yeah.
So one thing that wasn't on your graph at the end that I'm wondering about that maybe your methods are applicable to is another place where non-convex objectives come up in machine learning, which is whenever you're dealing with latent variables and you want to maximize likelihood of data that's incomplete. And so I'm wondering if there, maybe there's a reduction from those kinds of functions back to something more like a neural network that I'm not aware of. But I'm wondering if anything you've said ports over to that situation where we just have, say, a hidden markup model or some other hidden variable model that we want to maximize likelihood for.
So I guess the question is whether, actually I'm not quite sure I understand the question, so.
Let's try it again. So you've given us some nice claims and theory about what happens when you try to do non-convex optimization in machine learning problems. Mm-hmm. And you focused on a wide set of problems, a really nice set of problems that are important, like matrix completion and learning with neural nets. Another case you didn't talk about, and I didn't really see through your graph at the end, is just pick a model like an HMM. Okay. Or a topic model or something else that's latent and probably has a lot of local optima, mm-hmm. and might not have the properties that you're talking about. But I wonder if any of the tools you've given us can help us make headway in maximizing likelihood for those kinds of models.
Yeah, so I guess the question is whether we have worked on, or whether the techniques can be useful for learning like answer-based models with latent, latent variable models. I think we definitely have considered that. There are other, I didn't have any work on related to that, I guess, but there are other papers that shows that, for example, the landscape for optimizing the likelihood of mixture of two Gaussians has the same geometrical property. All of minima are global. For HMM, I think we don't know yet. I'm not exactly sure whether it does have this property. In the strict sense, if you learn it in a proper way, use exactly the same model to learn it. I guess we need to first try the experiment and see whether it works. But I do believe that some of the over-parameterization techniques can be useful, but I don't have anything concrete to say yet.
So it happens a lot in optimization that when you're trying to optimize a non-convex function, you can somehow change the variables or somehow so-called convexify it.
Yeah.
And so this happens a lot. And so I was wondering if something similar is happening here. Okay, the function is not convex when you look at it purely, but maybe if you change it a little bit or re-parameterize it in a sense, there is some convexity underlying it.
I guess the question is whether, in theory, in theoretical computer science, there are a lot of these convex fluxation techniques that can convexify the object function, and the question is whether there's a similar phenomenon here. I think, yes, definitely. So in some sense, this is kind of non-convex relaxation in the sense that you relax the object functions to some other object function which is not necessarily convex, but they are easier to optimize. Although, let me point out a difference between the kind of the settings we are talking about here and the usual convex relaxation techniques. So the difference is that in some sense here we have this, so we don't have to round back in, do the rounding step as in convex relaxation. So what we are doing is that it's kind of like it's a different way to think about the optimization, because basically what we did is so for example, if you give me a convex object function, and what I do is I go back to you and say, can you change your model and change your object function? So that's why I'm really optimizing a different object function, and I don't care whether I can have a solution to the original one. And in convex relaxation, what people do is that you convexify it, and it is a necessary step to go back to the original space and provide a solution in the original space. But here we don't have to do that. This is kind of a flexibility in machine learning.
Okay, so why don't we thank Tengyu again and